Hey, how are you? I'm so glad to be here back on this Global Hack Week. This will be my first for this AI ML week, but I love to give these streams all the time I can to try to help you or teach you new stuff. Previously, I had this beginner session for those who wanted to start in JavaScript, HTML, CSS, and MATLAB in the beginners week last month. But today we can continue with one of our favorite topics, of course, that is machine learning, artificial intelligence. And well, I feel so accurate that we split these two. We mention it in general terms, but we are going to focus on NND, right? Neural networks designs in this case. Um, hey, of course, I like to start reading some comments here. I just wish it wasn't 11 p.m. right now. Whew, it's a little bit late, I know. But hey, I'll try to find some better timing for the next sessions, right? Hola, Alberto. Hey, Moses. I'm thinking your name is Moises or something because I saw on Discord. Yeah. But hey, hola. Hi, Alberto. Hi, Alberto. Nice. Hey, I like to be welcome like this. I love it. Can anyone tell what's the best use case of MATLAB? Well, MATLAB, we can discuss this a little bit later. Give me a second. I'm the only one hearing mic echo. All good now. Oh, okay. I was worrying about that. But okay, if that's okay right now, I'm thinking it was just a connection issue or something like that. Um, yeah, returning to what I was saying, in for example, last Global Hack Week, I give a session about an introduction to MATLAB. So if you have any further question for this specific language or tool, you can check that session. You can always find the streams and everything in GHW.MLH.io. There you can watch all recordings from previous streams. What's the basic use? What is the best use case of MATLAB? It's very, very powerful for maths, I have to say. Um, since it is a language that it was thought, sorry, for being as the name says, a matrix laboratory. It's very well performed during. It has very good performance for these operations. There are some things to have in mind and to be considerate of with working in MATLAB. One, it's that it's a proprietary software. That means it's not free to use. It's not open source. It's not like, for example, JavaScript or Python. Um, since technically, if you want to be very purist, MATLAB is not a language indeed, but it is a complete suite. It has its own IDE, its own compiler, its own toolboxes, other tools like Simscape, for example, all in global for the MathWorks company, right? So it's a software you have to buy. In this case, since we are students and we should, we probably from our institutions and so have access to this very powerful tool. If you don't, if you're not a student or you don't have access to MATLAB, for what I know, here at the global, in the Mayorly Hacking, we give you like a 3 month trial or something like that for you to test. Um, but yeah, in general, for maths, for all matrix computing, for artificial intelligence, computer vision, a lot of stuff. So it's not only one use case. for control systems, it's very, very good. I have to admit it. But it's there's something that you can do in MATLAB that you cannot do in any other language. The answer is no. Don't worry. You can always watch me doing it in MATLAB, and you can do it in Python, for example. Actually, I plan to start doing more of these streams in Python in the future, because I do want to learn a little bit more Python and make myself more skilled in that language. So why MATLAB? Why Alberto is choosing here MATLAB for doing this? Well, the answer is because I I kind of like how the language. I kind of like how it performs this type of operations, the fastness, and how to say it. Uh, yeah, I think it's easier in MATLAB to do certain things. For example, I have tried to. I'm working on replying some, sorry, on translating some of my codes in MATLAB to Python, and I realized that I have to add more libraries, have to do like middle tasks that in MATLAB it's just two, three lines. In Python it's like 10, 5. It depends a lot. But yeah, that's the only reason, don't worry. Hello, sir. Hello. I remember from the first stream you introduced scripts. Will you be reviewing that today? Um, I remember from the first stream you introduced. Okay, yeah, we're actually working on live script. But hey, the important thing here again, it's not the the language or the tool we are trying to use. There are plenty tools. The important thing here is neural networks, MLP, as I mentioned in the announcement on Discord, which stands for multi-layer perception. So in Data Week, the last year, I introduced you to some of the neural network architectures. I introduced you to the perceptron, which it's not the first. Actually, the first neuron it's a little bit more simpler than the perceptron, but for practical reasons, we can consider perceptron as the very first and the minimum architecture for neural networks, right? We also review um, Hamming network. Yeah, sorry, I was thinking of it. And Adeline. And in Adeline, we introduced one thing called the learning principles, right? So perceptron and Hamming were networks designed fully for us to tune like manually. Again, if I mention some concepts that you're not familiar with, don't worry. Please just ask me in the comments because I'm assuming at this point that you already watched the previous videos I am mentioning, the perception one, the Hamming one, and the Adelan one. If you haven't, don't worry, stay in the stream. I will try to recall some of the important concepts. But if you do want to get the full experience and stuff after the stream is ended, after the stream has ended, go to the recordings, and really, really encourage you to watch those videos. I think it were really good, and well. Of course, I will try at some point to revisit them and trying to improve my explanations there. But at the moment, I want to continue. I want to teach you more. I want to teach you the next step, which is the multi-layer perception, right? Hey, I'm not a student and I will need to access MATLAB through the trial offered by the MLH. Is it too late to ask to sing up now? I don't think that you will be able to do it like on the time the stream it's being recorded. But don't worry, put attention here, and start the application process, and once you receive your response, you can rewatch the stream and with all the calm in the world, try to repeat what I'm doing here. Right? Don't worry about that. So nothing else. Let me start showing my screen, and we will start with this session. Okie dokie. Yeah, nice. So this is my screen. Let me move myself here. Okay, and all the all these streams I'll be giving, it's based on this very beautiful book called Neural Network Designs. Right, the author is Hagen and Bale. You can look for this as Hagen Neural Network Design, and you will find it. Don't worry. Actually, I think I shared a copy of this on Discord. But hey, it's completely free for you to download directly from the author's page. So don't worry, you just need to Google it, and that's it. I just saved you like 2 clicks that time. This time you will have to Google it. um, and for example, in this, we we again we already cover what neuron is, like the mental model, the mathematical model, how we take the inspiration from biological neurons. We also talk about the hey, thanks a lot. Yeah, here's the PDF. Thank you. I'm using MATLAB Online, which is free for 20 hours a month. Have you? Oh, that's really nice. I didn't know this actually. That MATLAB Online was free for 20 hours a month. Um, so nice. Thank you, Moses. Um, so yeah, thank you. Uh, 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 yeah, well, we're talking about what we already covered. These examples, we take these from the Hamming network, the perceptron. I think we also covered Hopfield network. Also, I wanted to share this, which is a repo where I'll be posting all the code. Right now, there's only the code from previous sessions. At the end of this session, I will share the code from this specific session. Um, in the MLP folder, of course. If you open the GitHub link, you will see that it's the Adeline, Hamming, Perceptron folders, manual example as a live script, and that's it. I haven't added README. I'm so sorry about that. I'm working on it, but yeah, that's a lot of thing to work on right now. Yeah. So the thing I want you to have in mind right now, and why it is important MLPs, and why this was like a big breakthrough, it's that remember for these examples we were designing networks that can do classification tasks. In general, we can think of neural networks as having two modes, classification and prediction, right? So in these scenarios, we were giving these neural networks an input, and we wanted them to predict an output. But the choice of the values of the weights and the bias and the activation, like the transfer functions, we designed it all that. We make all the data and the mathematics for being able to do that. The breaking change with neural networks and why they are so powerful was because of the introduction of the learning rules, right? So we just not need to design them for a specific task or for a specific classification. We can create big architectures and then train them to predict based on different data sets. That's the classic, and you probably heard of this. Um, sorry, I forgot the word of that. Uh, uh, supervised learning, sorry. Yeah, because we enter like the input and the expected output, so the model itself it's going to be adjusting the weight and the bias values and many other parameters in there to fit the specific or the desired output. So um, we can later talk about techniques and stuff, but the main idea it's that, right? And one problem, one big problem that we encounter during those tasks and the things we already do is that with those simple architectures we have checked at those moments, we can only solve linear separable problems. Um, if you're not that familiar with the term, that means, for example, if you have a graph that actually, don't worry, I will give the in a visual representation. I just want to get to the point that we introduced the backpropagation in multi-layer perceptions, and that allows us to solve linear separable problems, non-linear separable problems. I'm sorry, um, and more. We now are going to start with not just classification, but prediction. I think that we haven't done this far. So we are building our knowledge from scratch to become neural network masters, right? Um, Artificial neural networks, of course. So let's jump to chapter 11, which is the one we will be reviewing today and tomorrow. And let's see what I have prepared for us. In general terms, again, the important things to remark is that we previously saw in the Adeline one the LMS algorithm, um, least mean square. So the again the problem with this is that it was very specific. It had the issue that only linear separable problems are the ones we could solve, and that's it, right? So generalization of that. Here it's where they talk about this. Okay, the difference between the LMS and the backpropagation. It's only that the way and the way the derivatives are calculated. So the backpropagation it's a generalization of the LMS, right? For single linear network, the error it's explicit limit linear function of the error weights, blah blah blah. This will make sense once you check the previous streams, or again, if you want to take a look to this book, it's really beginner friendly, I have to say. You will again chapter by chapter be building the knowledge I am trying to express here. Um, Again, don't feel shy. Just comment or give me the question. Hey, what do you mean with this? Right? For example, what's LMS? Again, it's an algorithm we reviewed previously. Back preparation. It's the generalization of that, and it's the thing that gives power for this multi-layer perception. The perceptual learning rule. Blah, 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 designed to train a single perception network have discussed in previous chapters. Yeah. Apparently, this first description. Okay, this is more like an historical introduction. Okay, multi-layer perceptions. This is how they look like. So let's remember a little bit of this notation. Um, this is the inputs. We have a first layer will be the input layer. We have the next one. We were used to just working with a first layer and the output, right? So the difference between the one thing we already checked that it's the single perceptron and multi-layer perceptron, it's the number of layers, as the name says, don't worry. But a single perceptron can have multiple neurons, and that's a different thing. So Imagine them as matrix. That's why also MATLAB is very, very good for doing this. If you have a matrix, imagine the columns as layers and the rows as the neurons. So in this case, for example, we have one, two, three R neurons, one, two, sorry, one, two, S. Sorry, here's the S stands for the neurons. And this superindex doesn't mean that it's going to be elevated times one or elevated the square or cube, etc. It just means it's the number of the layer, right? So, and it's the operation inside this that gives the weight times the bias. Sorry, weight times p plus the bias. It's n. So this is going to be n, and the output of all the layer, it's going to be the output of the second layer, and the output of the second layer it's going to be the output of the previous layer, and the previous and the previous and the previous applied to the final transfer function, right? So we take the inputs, we multiply inputs times the weight matrices, we add the bias, and we apply the transfer function. Is it possible to have different transfer functions in the same neuron? Yeah, it is. Like, technically is, but it doesn't make that much of sense. What it's more normal is to have different transfer functions in different layers, right? So, for example, here f could be uh, log segment, right? And in f2, this transfer function could be hyperbolic tangent, something like that, right? The third layer, and in the outputs, it's this third layer. In this specific case, it's the output. Probably it will be something like the linear output, just like that, right? Again, it depends a lot of the architecture. Remember, some of the rules from the Wheatrow, for example, we have a competitive transfer, competitive transfer function here on the last layer. But hey, in this case, for the multi-layer perception, what it's normal it's to have in the last layer just a linear transfer function, right? In the previous ones, we could use logsig or tangsig. Um, and, well, I see we have some comments. Can you explain what would go wrong if we, one, only had feed forward propagation and not back propagation? Two, only had back propagation and not feed forward propagation, if that's even possible? The the quick answer for the second one, it's no, we cannot have just back propagation without feed forward, because to calculate the feed forward, to make the calcul for the back forward propagation, we need the results of the feed forward. And if we just have the feed forward, then it will be almost impossible, I would say, for the network to learn. That's what actually this is the learning rule for the MLP. So remember, for the align, for example, and yeah, if I'm not remembering well, it was add-on. We have the learning rule LMS, and in that case, in this case, the back propagation it's the generalization of that. So without back propagation, the network doesn't learn. So that's the what happened. If we only have feed forward, the network never adjust their weights or biases, so we just have outputs. Actually, we can run an example about that. It's interesting, because network will never learn. That's the answer for that. And the second, If we only have backpropagation, that's not possible because for backpropagation we need the result of the feed forward. Matrix columns are layers, rows are neurons. Yeah, exactly. Um, Index superscript indexes the number. Okay, yeah, good notes here. Multiply inputs, tying the weight matrix, add the bias, different transfer function in different layers. Transfer function example, hyperbolic tangent. Yeah. What do you mean by competitive transfer function in the last layer, Alberto? Um, for example, here, the network will probably will have at the very end just one neuron with the linear output, meaning that the result of that will be the, for example, in a prediction case, if we try to reply a signal, that will be the values for the signal. Uh, in remember in Hamming one, we had many neurons giving us, for example, an array of four elements, but we had to choose which of these were the class depending on which were not zero. So that means competitive. The values are competing each other to see which of them it's going not to be zero. So imagine we have two classes. So we have an array of an output, an array of two numbers, one being zero and the other being not zero. That means competitive. We can apply this to any length you want, an array of four elements, of six elements. That means we have four classes, six classes, etc. And to do the prediction in this case, it will predict based on the value that it's not zero, and the position, first class position, first position, second class second position, third class third position, and so on and so on. There are other architectures, for example, that gives you probability or chances, right? For example, you've probably seen these apps that you take a picture of something, and it tells you like, I'm 90% sure that that's a water ball, right? Or but it's still a chance for a reason for of the network that that's 10% of rocket or something like that, you know. That's what I mean with competitive. um, Thanks, Alberto. We'll keep in mind that backpropagation relies on feed-forward outputs and it's needed for learning. Yeah. Hey, for nice to see you. Hey, Alberto. I was going to sleep, but I have to jump and say hi. Hi, nice to see you around. Hey, hi for hello. Oh, also, yeah, there's really nice community here. So I like you to say hello to each other. It's just so nice. Let's continue with this. We already checked how this um, visual representation is. Remember, have in mind we can have as many inputs as are, as many neurons in a layer as s. S means the number of neurons here, and number in the upright, it's the number of the layer. The number in the bottom right, it's the number of the neuron. So, for example, this is the weight of the first layer for the first neuron. This is the bias of the first layer for the first neuron. This is the bias of the second layer of the second neuron, but this is the bias of the second layer of the S neuron. Yeah, we can define how many neurons we want in our network, right? I was waiting for your signature MATLAB stream. Yeah. Again, I'll probably change that in the future, in the near future. I mean, I will still love MATLAB, but I want to do a little bit more Python this time. So We will see. We will see. We can mix one Python, one MATLAB. We will discover that. But hey, remember, there's just one language in my heart, and that's it, JavaScript. Oh no, right now I have a Pikachu, but you get the yellow. Yellow is for JavaScript. Mm, um, good night, sweet dreams. Okay, so let's return with a pattern classification example. Remember, there were a task we couldn't achieve in the previous networks that we review, that it's an XOR gate. What is that? Because we have a zero here, a zero here, one here, and one here. And as you may remember, we can only draw one division here, that it's the decision boundary. In the previous perception, we just we can only draw uh, a decision boundary in any the 2D space. Well, try to with just one line divide these elements to be separated in circles and squares. A hint, it's not possible. But with multiple layer perceptions, we can do that because we can add many other decision boundaries. That's the magic in this. So the result it's going to be that now we can recreate an XOR gate with with neural networks. It's that powerful. Well, it's like it's an overkill, I would say. In Mexico, we have like this common say that it's like killing a fly with a rocket or a grenade or something like that. But hey, you can do it. It's possible. So let's review the code for doing this. And I want you to take a note to this little notation here that it's, for example, 2, 2, 1. In these representations, we are saying how many layers and how many neurons. The first number, it's for the first layer. So in this case, we have 1, 2, 3 layers, one input, one hidden layer, and one output. The input, it will have two inputs. Here, for the very first, we're not specifying the number of neurons, but we're specifying the number of inputs. So we will have two inputs. We will have two neurons in the hidden layer, and we will have one neuron in the output layer, and it will give us the result for this, right? So let's make a quick break and start opening your MATLABs because we're going to start coding, right? So give me a second and I'll be back. Hey, I'm back. So, yeah, let's open out MATLAB, and I'm going to open a new example here. And this is a live script for Moses you were mentioning. Yeah, I missed this comment. Read two inputs, specify a number, one hidden layer. Yeah. So, an exercise for you. If I mention an architecture, uh, 1, 14, 12, 2, 1. No. What does this mean? Give me the result in the comments. And meanwhile, let me check here how we are going to build this. First, we need to build our trending set, right? So that will be P1 equal to 0, 0, the output, the input, 0, 0, and T1 it's going to be 0, right? And same for T4, except that T4 it's 1, 1, 0, 1, and 1, 0, and these two are ones. This is P2, T2, P2, sorry, 3, and P3. Nice. Come on, give me the result of the architecture. What do I mean with what this one stands for? Actually, the question is how many layers and how many neurons have the second of the have these layers. Meanwhile, you answer that. What else? Okay, we already built our training this problem. Blah blah blah. So let's build a network. In this case, we have the resulting two-layer network. It's the overall design for these functions shown in the left figure. Inputs, decision, and operation. This it's built with function that it's what's the I forgot. Okay, let's return to here we are some mm, for the transfer functions I cannot remember. Yeah, here the Harlem. Okay, yeah, I forgot the icon about that. Yeah, okay, so it's Harlem. Let me note that. Nice. So now let's return to 11. Still trying to set up MATLAB Web Bus. Okay, don't worry. Um, Remember, don't try to focus on the uh, coding right now. If you want to put more attention here on this on the stream, and later you can do it. Don't worry. I will give you the answer for this. How many layers? The answer is 3. But hey, I see 4 numbers. Yeah, I told you the first one it's just for the input size, right, and of the input length. So uh, technically, this it's just saying that we are going to have just one input and two hidden layers, and one output layer. So this is the one here. So to identify the structure will be some follow a shorthand notation there, where the number of inputs it's followed by the number of neurons in each layer, right? So this is very similar to what we had in the architecture we were checking. We have the inputs. In this case, p it's just one because it's one. The S in the second layer, sorry, in the first layer, it's going to be 14, and S in the second layer, it's going to be 12, and S in the third layer, it's going to be just 1. An architecture that looks like this one, it's going to be 2, 2, 1, right? Because we have two inputs, two neurons, and in the first layer, and one neuron here on the output layer, right? So that's it. For multi-layer perception, first number specifies, okay, yeah, notes. Huh. Overall decision regions for these networks shown in figure in the left margin. The shaded region indicates those inputs that will produce the network output, right? So see problems P11, and for more on the multiple layer pattern classification, let's review that. Chain rule. Okay, let's summarize the backpropagation algorithm. The first step, it's going to be, okay, um, we will need to define a W1. Well, no, that works. Uh, mm, Batch, using backpropagation, choosing the architecture, blah blah blah, convergence, generalization of this, summary. Okay, so here there are some of these sub problems, right? So P11 and P12 were these linearable separable problems. So let's try to reply to make them in code. Consider two classes of patterns in that are showing figure P11, so class 1 and class 2. Are these categories linearly separable? No. Let's begin by converting the patterns to vectors by scanning each 2 times 2 grid on a column at a time. This would be 1, 1, minus 1, and minus 1, minus 1, 1. Okay, yeah. So let's do that in code. Uh, let's delete this. P1, it's going to be 1, 1. Minus 1, minus 1. Yeah. B2, it's going to be minus 1, minus 1, 1, 1. B3, it's going to be minus 1, 1, minus 1, 1. Oh no, this is P4. And P3, it's going to be the opposite, 1, minus 1, 1, minus 1. I'm transposing this since there are many ways we can write column vectors. I could just simply do this between every value, but I don't know. I don't like that. I prefer just to write the row vector and then transpose it to be a column. Um, it's totally valid. Depends on your taste. In order for these categories to be label, we must able to place a lane between the two categories. This means that the weight matrix and bias such that this and this condition can be converted to multiplication of the matrix. These first two conditions reduce to the state, which are contradictory. The final two conditions reduce to this, which is also contradictory. Therefore, there is no hyperplane that can separate these two categories. So, for solving this, there are many different multiplayer networks that we use to solve this problem learning. We design a network by first nothing uh, that for the class 1 vectors, either the first two elements of the last two will be 1. The classification vectors will alternate in 1 and minus 1 patterns. So this leads to the network we're showing here. So what will be the representation for this? 4, 2, 1, right? So why not? We can write that. Now, so we have it. This first neuron in the first layer, it tests the first two elements in the input vector. If they are both 1, the output is 1, otherwise, blah, blah, blah. So uh, let's do that. Let me check some little bit of what I have here because I need to refresh my mind. We will discuss this later, but I needed to, yeah, just wanted to have that in mind. Wait, it's going to be once of the length of good question. Oh, so in this case, there are not fully connected. They're only connected to this. So we need just to multiply 1 and 2 for the first and the 3 and 4 for the second neuron. So wait, I thought that. Oh, sorry. Wait, I thought that perceptions were designed to solve problems by adjusting weights to maximize difference between two groups. Example, positive group and negative group. It's that a wrong intuition? Uh, it's not a wrong intuition, I would say, but it's not, yeah, it's not fully how they work. Like, perceptions are, I would say, in general terms, I'm sorry if that sounds silly, but neural networks are designed to solve a problem. So it depends on the problem you want to solve, and same as in many other things, they can be different, very different ways to do them. So, for example, actually, that's what they are mentioning here on the text. There are many different multi-layer networks that could solve this problem. Actually, we can pass, for example, all the inputs to all the neurons. That's a fully connect layer. Um, and then adjust the weights and at some point, if we inspect what the network is doing, we can realize that, for example, uh, the learning process taught the neuron that just comparing the first two and the last two will give you the result. But since we know how logic gates operate, we can in well we can learn that truth, right? So we can, it's intuitive for us as humans. So we can design the network from the beginning to just do that, to pass the first two inputs and the last two inputs to different neurons, compare the results, and then compare them again to see which class we're trying to identify. um, so yeah, there's no big problem with that. Actually, I was talking about the logic gates, right? But now I was trying to uh, reply this. Let's return to the previous. Sorry for losing my train of thought. Let's return to the previous example of the XOR, because yeah, no worries, because I think with the full connect layer, it's easier to understand this. So here, as you can see, there's only two inputs, but all the two inputs here are connected to all the two neurons. So there is nothing like just P1 connected to the first neuron and P2 connected to the second neuron. That's well, that that's again not a wrong perspective of a wrong intuition, but it's just simply there are many different approaches. So that's it. um, yeah, for this, let's check this. Okay, so in architecture we already covered this, right? So it's right, but in order to continue with an functional example, we need to understand now how the back operation works. And the way they explain this here in the book, it's that we use this for a function approximation. So to make this work, the input is just going to be one complete signal, and the hidden layer is going to have two neurons. The output layer, it's a linear layer, as I was mentioning. We have just purling, and the log sigmoid, it's the transfer function they are calling here. So in this example, we try to replicate this function that we see over here. There are many ways we can affect the result of this. For example, in this matrix of different graphs, we can check how the bias of the first layer of the second neuron can affect, depending on its value, the position in time. If the x, if the x it's representing the time, for example, we can move this first volley, right? This first log segment, right? For example, the weight of the second layer of the first neuron, it's going to directly affect on the, how to say this, the curve that it's going to take the signal at the very least. So with a normal value will be as it is the blue line. But if we inspect, we can reduce it, we can completely flatten it, we can even make it the other side until we do like a mirror effect. The bias of the second layer is going to move the default function not in the x but the y axis, right? And the weight in the in the second layer, but in the second neuron, in the first neuron, no, yeah, it's going to do the same effect that the previously we mentioned, but it's going to make it sooner. So it's going to affect more the rest of the signal, right? That are just little examples on how we can start affecting these signal adjustments. But what we really try to do it's that the signal it's more like the input we want, right? So we want to stick to the blue line here. The backpropagation algorithm, it's again I mentioned it many times, generalization of the LMS algorithm, and the way we change things here, it's now how we calculate the derivative of the transfer function. So let's see that let's recall again that the output of the first layer is going to be calculated for doing the weight time the input plus the bias, all applying to the transfer function. And the output of the second layer in a feed forward normal workflow is going to be exactly that for the first, replacing sorry. So the thing is that you can imagine the second layer being exactly the same as the first, but instead of the input, you have the output of the first layer. So see how we change P here from A1, which is the output of the previous layer. And for the last one, it will be the same. Instead of P, we have A2, which is the exactly directly previous layer, right? So the performance index, as we were discussing, we will try now to backpropagate. Imagine you pass all the data, and it's very simple because of the name. List means squares. Yeah, exactly. LMS, sorry, it's list means squares. Um, so yeah, you pass all your data through the network. So it starts as it enters, then it's changed in the first layer, then it's changed more in the second layer, and it's fully changed in the third layer. And now we need to calculate the error for that. So in least mean squared, it was simple because we just have one layer. So we just have to adjust the weights and vectors of the biases for just a single value of, well, not a single value but a single dimension of the of the neurons. Here the complicated thing starts because how the information of the last layer, and this is just three layers, imagine a much wider one, can pass all the way through the last layer, through the first layer. Well, for that we apply that derivative. So we apply something called the change rule to make these derivatives. If you're not familiar what this is, it stands for, you have two functions, df of n of w. Then you separate them, saying the derivative of n depends of, sorry, the derivative function of n, um, the n, it is the derivative function of n, which depends of w. So, for example, if the function will be the e elevated to n, and n it's to w, so that the change rule applied here it will be then the division of the first derivative times the second derivative. So the derivative of en, it's still en, and derivative of 2w, it's just 2, right? So we can multiply these two and we'll have the chain rule complete. If this math doesn't make sense, or you want to take more explanation on the mathematics, I I think this book lacks of more deeply explanations here. What this book explained very well in maths, it's like the yeah, matrix operation, vector, state spaces, and stuff. But yeah, this is all they have for these derivatives. But don't worry, just trust me in this. It's easier actually if you do it in code because you can, well, you just have a limited set of transfer functions, and you can look for the derivatives of these transfer functions in tables. So I will show you, for example, a piece of code that I have here, in which I say, for example, purely it's just y equals x. If I apply a derivative to this, it will be just one, right? So I saved it directly on a function. So I just not need to perform this again. Thanks to the change rule, I can, for example, if in the first layer I have logsig, and in the second layer and the last layer I have purling, then I can just multiply the derivative of this and the derivative of this. That will be these two functions being multiplied, right? So in code, again, it's a little more simpler. Um, but yeah, and these ones you can find in many tables, right? So don't worry for that. And well, doing many math, we realized that the metrics for this become these functions, right? So the weight matrix, it's for the update, or the new weight matrix, we will have the previous values minus the learning rate times the sensitivity. In this case, be cautious, because yeah, I do agree S was not the best choice, since S in the architecture mean the number of of neurons, but here S doesn't mean the number of neurons. Be aware of that. It means sensitivity, and it's a value we are calculating later. Don't worry. Times the output of the previous layer transposed. That's what this T means. And for B, it's the same. The new value of the bias, it's going to be the previous value of the bias minus the learning rate times the sensitivity of the layer, right? What's the sensitivity? Well, sensitivity is the partial derivative of the layer transfer function, and that's it. Well, it's not that. Previous values times, yeah, okay. Um, So that's how we propagate this, right? Sorry, that's how we calculate this, but we need to back propagate that sensitivity. So we have a matrix of these partial derivatives. We can call this the Jacobian matrix. This is also very commonly used in control systems, but don't worry again. We can reduce this thanks for all the math these beautiful people does for us. We can reduce this to a function. Then again, it's easier to program in programming languages, right? Because it's the derivative of the transfer function, this f with the dot on top, that means the first derivative, because we can have many derivatives. First derivative multiplied by the layer output times the previous weights values times the previous sensitivity. That's just it. And well, again, many more maths. We they define a sensitivity value for the general layers and one specifically for the last, in this case the first sensitivity, last layer, first sensitivity we're calculating, because remember we pass forward and now we are going backwards, right? So for calculating the outputs, remember, uh, we get the inputs, we calculate the first layer output, we pass it to the second layer because we need it to calculate the second layer output, we need it to calculate the third layer output. Now we calculate the sensitivity of this last network, of this last layer, and we start back propagating. And the sensitivity, you may remember, it has the value of the layer the output of the layer we are standing. For the last layer, for the first sensitivity we calculate, it's just minus 2 times the derivative of the transfer function. A little hint here: the derivative of the transfer function in the last layer, for this specific case we're mentioning, this is always 1, because since it's the derivative of sorry, forgot the name, of the pure link. So this will be minus 2 times 1 times, it doesn't, the output here, uh, times the error. So the error, it's really easy again to calculate. It's just the target minus the expected output, right? Sorry, the real output. So it's expected output minus the real output. And for the rest, now we have the derivative of the transfer function times the output of the layer times the weight matrix, um, times S. And that's just it. Now, finally, they mention again the values for updating the the the, the weights and the biases. So um, this is an example, blah blah blah. But let's do that. Let's start applying these. I'm going to copy this, which I had prepared, and put it here. So A1 the only thing is that the transfer functions are not the same, right? So for all of these transfer functions, in this case, these are all going to be hard limb, right? Yeah. So hard limb and hard limb. And for the derivative, it's going to be Harling derivative and Harling derivative. And now we need to add that, of course. The functions for Harling, I have it here. For example, let's say that you don't know the derivative of this. So you come here and you say hard limb transfer function, and it says force a neuron to output 1 if the net input reaches a threshold. So in this case, we will define that as this. Hard limb of x, y equals, okay, if x it's bigger than 0, y it's 1, else y it's 0. Nice. So what will be the function y equals the hard limb derivative of that? We return and they say derivative of hard limb transfer function. The hard limb in our example, derivative of transfer function in the last layer, it's only one purely. Yeah. Thank you so much, Silbert. I have to go now, but it was a great session. Oh, okay, don't worry. I hope you can catch later the recording for this. We will still are checking the um, signal, not classification, well, prediction, not classification. And tomorrow we will reviewing now training and how to make this on bigger scale. We're going to check about early stopping and batch training for doing these like in real world scenarios, not just logic gates and simple tests, right? So stay tuned and come back tomorrow. Yeah, I think. Yeah, I cannot think of what the actual derivative of this can be. So that's an interesting thing. Yeah, let's ask chat GPT for that because that will be. Do you know Harlem TF? Yes, Harlem. What would be the derivative of that? Yeah, yeah, of course, it doesn't make sense. Oh, this is interesting. Not using in batch propagation. Okay, well, interesting. Um, okay, let's just then, if we're not using the derivatives, that means we just are going to apply the um, yeah, the feed forward. So weights and matrix, right? So weights. Oh, we need to weight. What will be the case? Oh, in this case, we don't have weights, and the bias it's -1 and 1. Okay, interesting. So this will just be. I popped back in to thank you properly for answering all my questions so patiently. I really appreciate it. Hey, yeah, don't worry. Buenas noches. Yeah, good night, good time zone, appropriate reading all. Buenas noches, Alberto. Yeah, for sure. It's almost 10. No, it's almost 12 for me. I will sure for yeah, I will tune for tomorrow for sure. Yeah, so I pop back. Okay, nice. Sorry, I missed that comments before. Yeah, the transfer functions will be one and two. We will get rid of these weights. The input will be, let's do input right now, p1, and this should be 0 plus the biases, and biases, it's going to be -1, 1.5. And 1.5 -1.5. Biases of 1. We remove the weights. So this is just going to be a 1. The error, we're not using sensitivity, and we're not incrementing this. So let's see what this has to offer for us. Okay, the error is not calculated like that. Hmm. Yeah, the target, it's T1. So error is 0 because target 0 and A2 it's 0. Yeah, it should be 0. And now if we pass, for example, P2 and P2 and T2, this should be 1 and error should be again 0. Oh, okay, this wasn't. Hmm. holding if it is not 0. Okay, input, it's, let's see, input time biases 1. That's this matrix, and applied to the transfer function. Of the input plus biases of 1. Okay, this is 0. And this 0 plus, so then A1 is 0. Okay, the thing is, it's probably making a wrong comparison here. So we need to sum this. Actually, make the sum of the input. Yeah, no, I don't think that will be. One. Okay. Let's perform this individually, since this is a 1, 1, and we are going to have a 1, 2 of the second neuron. This is going to be the sum of this plus the biases first, the first value. That's it. Minus 1. Yeah, exactly. And this is going to be the transfer function of the first, yeah, row, some input plus biases to second value. Okay, let's see how that behave. We have 0 and 1. And doing this, we have 0 and 1. Huh. We make the sum of 1, 1, 2. And 1 plus a 1, 2. This is 1. And we multiply. No, we add this. A 1, 2. Okay, if I add biases 1 minus, yeah, it doesn't make sense because, oh no, yeah, this is the weight. Yeah, we do need weights. I was curious about that. So let's run to that. Weights. Sorry, I forgot. No, there are here. Where I put them? Yeah. Okay. Yeah. So yeah, remove the weights. So sorry about that. But yeah, we need them. Same as here. So weight for this. Oh, okay, we have two weights. One being 1 1 for I think 1 1, and the other one it's going to be no. It doesn't make sense. This is 2. What this stand for? Let me check. For example, I want to check again this architecture to of dimension. We're talking here about dimension. No, because these are 4. Yeah. So, yeah, we are talking about the weights. This is 2, 2 minus 1 minus 1. This is going to be multiplying weights 1 weights of the first row of the second row. Okay, now nice. Let's test it with the tree. again, and let's test it with the fourth. 0, perfect. Yeah, we were missing the weights. So if this goes to 0 here in the first, then we have nicely done. So now we have it. Amazing. Um, Let me break for it to you. So I will explain what I'm doing here. But basically, this it's our neural network that replies the behavior of X or gate. You see, we pass 0, 0, and it is 0. We pass 0, 1, and it was 1. 1, 0, it was 1. 1, 1, it was 0, right? So amazing. If we want to inspect it more deeply, we have again 0, 0. The final output is 0 and the error is 0. The and what we're expecting right now it's a 1 because we are doing this with 1, 1. The output again is 1, so error still 0. This is 1, 0. Target it's 1. Nice. And for both 1, 1, this should be 0. So we can run this. And the output is 0. Right? Nice. So, first we define our prototype vectors. In this case, we are not training anything since they already gave to us the full architecture for this, containing the weights and the biases. So remember that. Um, if we wanted to start from scratch, like with from random values of weights and biases that will be training the network. We will be covering that tomorrow. Don't worry. Actually, we're going to get a taste of that today for the function approximation. But for this, just for you to know that we already overcome the problem of having not linear separable problems. You see, as this graphic shows, we can now separate these two values, right? Perfect. Um, Transfer functions I define as Harling. Actually, this is just this is again it's a little bit overkill because I'm defining cell structure being for the first layer the Harlems and the second layer the Harlems again. In this case, both are Harlems. So don't worry. The Harlem, it's this one. Yeah, I was thinking nonsense because one, I was trying to backpropagate and do a lot of things that we didn't need it because they already gave us the um, correct values for the weights and the biases. So just feed forward, like the question cell battery just asked me about what happens if we just do feed forward. Well, the network doesn't learn. We are just taking outputs out of it. In this case, it's what we wanted because we already have the weights, the values that gives the correct answers. So we have the inputs. The inputs we declare here. We have the transfer functions. The transfer functions we declare here. We have the weights and the biases that we have here. This is 2 times 2 oh, what happened? I think it blipped for a little, but hey, don't worry, I'm back. If anything with this stream, just let me know here in comments. But yeah, this will be a 2 times 2 matrix, and this will be 2 times 1 because we have to multiply R, R times S, which is the number of inputs times the number of neurons. So two inputs, two neurons, matrix will be 2 times 2. Two inputs, one neuron, matrix will be 2 times 1, right? So the values for these I put here. This will be the first weight matrix for the first layer and the weight matrix for the second layer. Biases, it's really similar. It's just 1 times S. So for the first layer, we have 2 neurons, 1 times 2. And for the second layers, we have 1 times 1, right? So simple. The input we try to test in this case and the target. A1, remember, and the functions were given in the summary here. We need to move a little bit over here. A for the first layer or the second or any are going to be the transfer function multiplying for the weights that multiplies for the previous input. So in this case, for the first input, in this case A1, it's going to be multiplying for the input plus B, right? So in this case, I probably just actually I divided it just for me trying to debugging what was going wrong. At the end, it returned that I was missing the weights because I didn't notice that. But we can do just a single A1, right? No worries about that. And that will be the weights multiplying for the previous for the inputs plus the bias and that all evaluated inside the transfer function. And that's it. That's just a simple feed forward rule. For the next one will be the same, exact same transfer function, weights multiplying for the previous input. In this case now, since it's the second layer, it will be the results of the first layer plus the biases, and that's it. And that gives us our result. So if you have any questions, just let me know. Let's make the adjustments for this for doing. Okay, let me comment this. I don't want to ruin everything. Okay, so A1 weights completely multiplies the input completely plus biases completely. And in here it's just A1. Does that make sense? Oh, what happened? Incorrect dimension. I'm probably I'm missing something. No, I'm going to transpose this just to see. Biases. Okay, let's debug this further. Okay. Okay, yeah. The input. It's the one I'm going to. Okay, nice. So let's try this. Okay, this doesn't work. So, okay. It's about the dimensions and stuff. But if this works, as good engineering, don't move it. We return to normal, and now it works. Nice. So let's continue with our next example, and let's just see this very quickly in order for us to have time for explain further tomorrow. But what we want to do now, it's a function approximation. We already overcome the problem that we were facing in the previous sessions about how to um, classify linear separable problems. Sorry. Now we can classify in more than that, and that means also function approximation. The second mode of the neural networks that we haven't reviewed yet. For this, we what we want is that given function, a signal, or neural network will reply it. We will do the same. And this is very commonly used in control systems. So again, we already are talking about real world scenarios, real use cases. So for doing this, we are going to apply what we learned about uh, the back propagation algorithm. So in this case, now we're doing back propagation, right? So let's review the example the book has to offer for us, and we are going to recreate this signal here. So let's do MATLAB very quickly for that. I have it saved here. So first, let's clear down the outputs here, clear the variables around this, and let's prepare our data. We're going to create a line space, which is a vector of 400 elements that goes from -2 to 2. That's the same as they're showing here, -2 to 2. Why 400? I can't remember if they mentioned something about that here, but hey, 400 is a good number. Then we create our g of p, right? Our g of p, it's 1 plus the sign of p divided in 4 multiplying p, which is the dependent variable, right? So p it's our value. We have 400 values of p. Since that, we will have 400 values of g of p. Now we create of polynomial, which is just the array of these two, and we plot it, and we also we need train data for the future, right? In this case, they are mentioned that the train data will be 21 values here. Next, we need to select our train set. For this, we are getting a sample of 21 points in the range of the full function, -2 to 2, equal to intervals of 0.2. For doing that, we select train set, train index -2 with steps of 0.2 until we reach 2. That gives us the 21 points we wanted. And the train data is just evaluate that same in the function that we evaluated p. We can create this as a function, but it's not that hard to copy and paste here, and it's the only place we're going to use it. So, don't worry. So let's run this little piece of code to see. And yeah, it's the same, and it's what we wanted, right? Uh, hey, show the plot. Come on. Let's save this. as what could be the name for this? Um, XOR example. Nice. So back to the book example. Actually, let's rename this as function. No, what was the word for this? Yeah, function approximation. Well, the function example. I forgot I was doing. Uh, but come on, Pascal case, camel case. I can't remember the name. Yeah. So we created our data. I don't know why it isn't showing the plot. Let's run this again, hoping to see the plot. Come on, show it. Well, I maybe need to restart MATLAB. Don't worry. Oh wait, time is running. So I will try to finish this quicker as I can. Come on, MATLAB, help a little bit. I just want you to see the same thing here about having to train and the examples and stuff, but now applying the backpropagation and how the weights and biases matrices are updated. And well, again, tomorrow we will discuss this deeper, and we are going to start applying some of the um, training techniques as the batch versus incremental training and the early stopping, for example. So okay, now it opened again. Who? Okay, yeah. Don't know why sometimes this happens, but yeah. So our blue line, it's the function g of p, and our marks here, the red ones are the training sets, right? So we define our functions. We define a network, same as the, well, similar to what we did here, but in this case we are adding a little bit more things, which are the initial values. In this case, we just give not initial values because it stayed the same all time, but in this case we have uh, other values that are used. The values are given for the example. These are minus 0.7, minus 0.27, minus 0.41, minus 0.09, sorry, 0.09, and minus 0.17. Same for B and, well, B1 and B2, right? So that's it. That's the initial values for this. I run this action. I have them. And in this learning example, they mentioned that we should use the 16th element of the training point. Normally, when training, we pass randomly the data. It doesn't matter the order, but in this case, I don't know why they choose this 17 point, which is the value of 1. According to this, the result should be around 1.7 0.7 or something like that, right? So the output of the first layer, it's calcul same as we already covered. Actually, the function I'm calling here, it's train specific. You will we will see why I call this train specific. But hey one, it's again transfer function, the first of the first layer multiplied by the weight of the first layer times the input, which in this case is 1, the train index 16, plus the biases of the first layer. Then A2, it's calculated the same way, except as passing the input, we are passing A1, which is the output of the previous layer. Then we get the error for the back propagation, because remember the sensitivity of the second layer, the last layer, it's going to be -2 times the transfer function derivative of the second layer. In this case, remember it's pure ln, so it will be -1. Um, passing the argument of the passing as argument, sorry, the value of the calculated output of the layer times the error. In this case, the error, this is writing the same. We could replace the thing between parentheses for error, right? Now we have the sensitivity of the last layer. We're going from last to first. We have to calculate the sensitivity of the first layer. And that's it with the derivative transfer function of the first layer, passing the argument of the value calculated in the first layer, times the weight matrix transpose of the second layer, not the first layer, times the sensitivity of the second layer, right? So now we have S2, S1, and we update the weights and the matrices, right? So these weights and matrices are going to be the previous values of the weight and matrices. Sorry, the weights and matrices, the weights and the bias. Uh, the weights and bias, the previous values, minus the learning rate, times the sensitivity of the corresponding layer. And for biases, that's all. And for the weights, we also need to multiply times the value calculated in the previous layer transpose. If it's the first layer, or I mean, yeah, of course, if it's the first layer, so there's no value calculated in the previous one, so it's the input. So that's why you see for the weight of the second layer we have A1, and for the weight of the first layer we have input, right? So let's run this. Okay, I forgot to run this. Oh, and I forgot to, yeah, of course, this doesn't give any, because I put this, I was making some test earlier before the stream, so that's why I needed to make these changes. So sorry. And I need to uncomment this and this. And now I run. And you will see these were the initial values of the W's and biases. And now the expected output of A1 and A2 are the same as the one in the book, 0.321, 0.32, wow, this is rounded, 0 to 0.368, 0.446, 0.446. The error is 1.26, 1.26 the error. Sensitivity value it's minus 2.52, minus 2.52, again rounded. As of sensitivity of layer 1 it's minus 0.0495, and well, you see the same. And when we update the weight and the matrices, we still get the same results of the book. um, 0.71, 0.171 rounded, minus 0.7070, well, 772, and etc. and etc. So time's up. I need to close session right now, but this was just an example of the very first learning of our network. We will give this much more power in order to recreate the signal. But that's for tomorrow's sessions, right? So, thanks for joining. I had a really great time with you, and I hope you learned something. So, if anything, just leave me a comment or look for me in Discord. See you tomorrow for the next part of this session. Thank you, lad. Bye. Hey, don't go. Actually, I was forgetting something that I was asked to not forget, uh, which is the survey for these global hack weeks. So please make sure to give us the feedback. You can go to mlh.link/global hack week feedback. I will share you the link. And please share with us all your thoughts about this session. And well, if you all watch any other and you didn't give feedback about it, give us feedback. We love that. And now that's all. Thank you.